But the really useful thing is that all the ratios of column densities and ratios of volume densities are the same. So actually, the idea is you don't worry too much about that. We're only interested in ratios. So the depth of the cloud isn't going to affect any ratios. Anyway, the rest of the formula, so if the telescope is seeing emission from the cloud, it's going to depend on a few things. It's going to depend on column density, that is how many molecules it's actually looking at. Okay? It's going to depend on the Einstein A emission constant, so the molecules are in there, but how many photons are they producing per second? That's going to affect radiation EG. There's also another term, H nu, and that's because the definition of flux isn't counting 1 photon, 2 photons, 5 photons. It's measuring the energy that it's receiving in the form of photons. So the energy E equals HF equals H times the frequency, means you have another H frequency in here. And before we get carried away about units again, if you use the technical units normally for this are ergs per second per square centimeter per steradian. But as long as you're aware because we're looking at ratios again, you can probably ignore most of those details. As long as you understand the physical meaning of all the terms, and the 4 pi is just a 4 pi. But the difficult part maybe is that, so this transition is j equals 1 to 0. It's the same one you're looking at. So I've written that as the flux 1, 0, because if you look at a different transition, a different emission line, if you look at the actual spectrum, so if that's the frequency, this is the flux, you'd see some kind of background and then the transition lines, like that. They might be 1 to 0, they might be 2 to 1. So the flux of each of those two lines is a separate quantity. So the reason we have to have, that means we have to have the column density, not just of particles in total, in the cloud, but particles in the j equals 1 level. The reason being, if there's so many molecules altogether in the cloud, it's only these ones that are going to decay and produce the radiation we see there. So that means that this column density is the column density of those excited levels, which you've now worked out a lot of things. You've now worked out the abundance ratio of the excited levels, so you can now work out the column density ratio as well. And then the way the question is, what it says is, which molecule will produce a greater flux? So more. So it doesn't even say how much actually, you don't need to calculate a value. But the question is, you might, for example, what is the ratio of these fluxes? Is it more or less than 1, which produces the most flux? That's kind of the question. And then you might find that because you're calculating ratio, all the constants and the definitions are not something. There's an equation for the flux, which is also in the notes, but there it is again. And so this is a good way to judge which is the stronger flux. So if you put this equation into there, then you'll start to see which quantities are affecting that ratio. So for example, let me delete this. We write this out in full for a second. It's a lot of terms, but you know. So all I've done is just take the equation for the flux and consider this ratio for everything that's calculated about CO and CS. And the idea is that we can simplify that quite a lot actually.
The question says the n are the same, or
It's it. Well, that's actually that's the point I wanted to make, was that the question says that. Well, what I meant by that was the total column density is the same. There's the same amount of CS and CO molecules in the cloud. So then to work out the density of a particular level, the density of a particular level, N1 is the one you want, levels that are here, then that's going to be the total column density times the ratio of the levels, the abundance ratio of those two levels. For example, in this case, the ratio is so over 3. But the total fraction of molecules in the N1 level, 2 out of the total 5 are in the excited state. So then the total amount of column density is going to be equal to, this is a mess. The total column density, column density of the excited levels is equal to the total column density times the fraction it wasn't going too well, but the idea is that you've already worked out that there's 2/5 or 40% of the molecules are in the top level. So the total column density times that 40% tells you how many total column density in this level here. So what that means is we have the ratio so okay. So the ratio of the fluxes depends on the relative Einstein coefficients of the two molecules, depends on their transition frequencies, because of that term there. And the column densities is going to be dependent on the total column density times the fraction on the excited level of each molecule, which you've already calculated actually. That's the information on your graph. And because I then said the total column density is the same, that cancels out. So because we're just looking at ratios, the conceptual idea is you just need to know how many molecules of each, how many excited molecules of CO and CS are there in this volume, and then modify that a bit because the CO and the CS have slightly different Einstein A coefficients and slightly different frequencies. That's the concept. Any more thoughts on that? I can explain it to you individually as well. Or in fact, any questions or anything else that you've already looked at in that exercise. Okay. And I'll go through the test answers a bit later.
So we're going to work on the assignment for the whole 3 hours? For the whole
have you finished?
Sorry?
Have you finished or never finished?
No. I haven't done the third exercise.
Okay, yeah, no, fine. And if you finish, I can even find you something else to do.
Okay, perfect.
It made some sense? Okay. You asked me anything. Yes, okay. So, yeah. So forgetting the equations, that's what confuses me. So you have two possible levels. We're ignoring everything else at higher energy. And you have so many molecules. And some are in the top and some are in the bottom.
Yes.
So, but what you've worked out here is at this point, 100% are in the top level.
And in this time, 100% are on the lower level.
Yeah.
Or in the CS molecule.
Yep. What have you plotted here? Log NH2 Y1 Y2 ratio NH2 ACO. So you've written a function called ratio.
Yes.
What is it?
This one.
1 plus. Okay, so that is that is the.
This is this equation.
Yeah, that's the two-level approximation.
Yes, that's the
Okay.
level approximation.
Okay, so if you do bring up that equation, actually, if you do have the notes there for. Yeah. maybe down actually. Okay, so there's two slightly different things here. Here you've got N2 divided by N1. So in that example, okay, here it says 1 and 2, but here it says 1 and 0.
Yes.
So this example, it's the top level is 2 over 3, right?
Yes.
So that's what that's calculating. But the bottom one, but the ratio, N1
over
is 2 over
N1 plus
5.
N2.
So one is telling you the ratio between the upper and lower level.
Yes.
But if you had 4 on the top level and 1 on the bottom, that number would be 4, right?
Yes.
So not between 0 and 1. But the fraction can only go between 0 and 1. So in your function the ratio, you're calculating 2 over 3.
Yes.
And on the graph, and in what comes out later, it's more useful to have 2 over 5.
But why I have here 2 over 5 if I'm plotting the ratio?
Right. So I think ultimately it actually doesn't matter. The graph is interesting either way, but I think in the question it asks for the fraction of.
Yes. What I'm doing in this equation is I'm calling this y.
Yeah.
And I'm calculating this part.
Yeah.
Okay. So if in the graph I'm seeing this, what I'm seeing is the ratio between the two.
N2 divided by
N2 divided by 1.
Yeah.
But how I can get N2 divided by N1 plus N2?
Okay. Well, what if that ratio doesn't matter? So, in fact, neither of those two matters exactly how many molecules there are. So you could, for example, say N2 equals whatever you calculate, and N1 equals 1.
Oh. And then I do the sum in the. I can then. Okay.
No, this looks good. You can see quite cleanly what's going on. I think it's okay. No? Probably that's hard to see. Yeah, no, I think only the x-axis is better. Okay, so now I'm a bit curious about the 0.5 actually. The graphs look like they have the right shape, I think, but why is it 0.5? So this is, okay, so can you show me where you calculate YCA? Okay, the function, okay. So this equation is h over 1 plus h. That looks pretty good. Yeah, that looks pretty good. See, yeah. Yeah, that looks pretty good. Yep, that's right, yep. That looks good. N1 and N. Okay, yeah, I see you. That's right. Yep.
And some
And you rearrange,
algebra.
and you get to this point. Cool. That looks pretty good.
X is this. X is this.
That all seems really, really right. Except I think the answer for some reason is not 0.5. So I'm trying to figure out where.
What is the value?
Well, it's a bit. It's actually different for both molecules, for one thing. So something is not quite. Let me check. Q. K. A. is good. So here's a question. Where is the temperature in this?
For the ratios. But for the ratios, I don't need.
There's, okay, so I can see the problem. Okay, so this is the physical picture of the two-level approximation. So this is A, right? The constant Einstein coefficient A that's the controlling this process. Then you have two arrows here going up and down. And so in this equation, do you like this kind of equation, differential equations?
Sorry.
Do you, are you kind of
I have to
something familiar?
integrate this.
No, but like, do you like this kind of equation? You've studied this? Yeah, okay. So the minus A to A is downwards, right? Minus A. Then NH to 1 Q12, that's the up arrow there. And NH2 into Q21, that's the down arrow there. So Q21 is two different convolutional rates. Because there's two arrows, there's the rate upwards and the rate downwards.
I only use one.
Right, and so actually in the equation it turns out they're both in there. So because Q12 is the upwards rate, Q21 is the downwards rate.
It's minus. One is plus and the other is minus.
Not exactly, because this is where the temperature becomes important actually, because it depends how, I mean the kinetic temperature, TK, that controls how fast they collide, right? And if they collide, if they can collide and spin faster, so if they collide and it rotates faster afterwards, that's the up arrow. And if they collide and then it rotates slower afterwards, that's the down arrow. And so there's actually a correlation between the two which depends on the Boltzmann distribution. So there's, yeah, okay, so everything is right except for that one extra thing.
Okay. This means this value is this.
Let's look at it. What did I write? Q12 or Q21? Yeah, so that's the same as Q. Well, that's Q01. So, sorry, I changed between 0, 1, and 1 and 2. Must be that one, yeah. Must be that one. Yeah.
And the other?
You need to calculate afterwards, yeah.
In one, I calculate the other.
Yeah, so they're related, but, and so that's why you need to know the temperature as well, because that affects. Okay, so one more calculation. Uh-oh. makes sense.
I don't know what's happening here. I have the new value, the frequency for.
Okay.
I'm searching for the frequency, and I have the energy. I'm plugging in the lamp's constant, but it doesn't work. I don't know why. And the equation is right.
So you see it?
This one. No.
Yep. Okay. So what? So which? This is for the first part of which? Yeah. Okay. So what units is C0 E10 in?
It's in. I closed the terminal. It's in centimeters.
Right. Okay. So that's already actually not an energy but a wave number. So in your equations, it's the wave number, not the frequency. So okay, but then so you're working out the energy. I'll be right back.
I don't know.
Okay, you see it. Yep.
I was struggling a lot with the last point of the first exercise.
Yeah. Okay.
Because I was obtaining some results that
No,
made
negative.
the excitation temperature negative, which obviously doesn't make sense. But we now figured it out, and they're actually positive, so it's okay.
Yeah.
But when I see this expression, it makes me think that you could actually get a negative excitation temperature, which obviously doesn't make sense.
What, but the complex energy?
What? No, because when you solve for the
Okay, I see. Okay,
excitation
I see.
temperature,
Yeah, all right.
it could be negative.
Yeah, that is possible. What would that mean in terms of the densities?
Or is there any like physical explanation or mathematical explanation?
What's that equation?
Well, this is lacking the G1 over G2.
Sure. Yeah. That's right. It is there.
It's a mess.
Let me write it down. Let me write it down.
Yeah. Okay.
Excitation temperature.
La gráfica que me dio bien.
Minus EJ.
Pero no sé qué tiene que ver, pero no sé qué
¿Qué significa?
No, no sé. No,
EJ divided
pero no
by.
sé por qué cambio, porque no voy a dejar.
So that's divided by.
Yes.
So G naught by. Maybe we'll go on the board. That's right. And then is that right?
If you let alone the exponential function, then you take natural log to both sides,
Yeah.
and then for dx, you
Okay.
have to put natural log.
Okay. So. Yeah. Okay. So a negative number would happen if this is less than 1. You get a negative number, right?
That's exactly my question.
So if you have a very high value of N1 over N0, you would have a, okay,
No, actually the other way. Ah, yeah. If that is greater than 1, this is negative, this is greater
Yeah.
than 1.
Including the effect of the degeneracies.
Yes.
So maybe what it's saying is that, I guess if you had the Boltzmann distribution, looks like this. And if you had a higher temperature, I guess it looks like this, right? That's low T and a high T. It gets wider and wider and wider.
Have you already explained it?
No, I'm not sure it's pushing else. No. So if you have a very high T, you get a much longer exponential Boltzmann function. So here actually, you're approaching constant, flat. So to actually have if you actually have, yeah, I mean if you have a very high temperature, then because this is going flat, you're having an even distribution among all possible modes, the middle end is much less than the temperature.
So it's never going to be actually...
So if you have a higher and higher temperature, you can never have more than the degeneracy would sort of average out to.
Okay. So it's never going to happen. It makes sense.
I mean, and it does happen in reality once you have optically thick conditions. So then you have photoabsorption and stimulated emission, and that can totally mess up those populations. But if the temperature is being controlled by collisions, then that's the shape of the function. And yeah, okay. I didn't even thought of that, but that makes
I like it.
We are talking about the question we gave you about the density of H2.
yes.
You asked here, first consider 10 to the 6
Yeah. Yeah.
second power.
Yeah.
But in the flux rate, we don't see where does the
Okay, yeah.
density
Good,
come.
that's a good question. So it doesn't affect A, H, nu, 4, or pi. Those are all independent density. So it really comes down to this one. And so N10, as I was trying to explain before, is that's the I've written down already. N10 is it's the total column density times the ratio of levels. And so if you change the density of H2, then all the levels, the ratio levels, the collisions will change. So the ratio of these levels will change.
I mean, one is always gonna be will have more flux than the other, right? Independent.
No, it changes. It can change over, yeah.
Okay.
Yeah.
Depending on the density.
But I guess the big idea of the exercise was, I mean, you observe flux. That's what astronomy is, observing the flux.
Yeah.
And so if you change the density, the flux changes, right? Well, as you were trying to ask me. So if you can see the change in flux, then you know what the density is. That's kind of the point.
Okay.
It's better to stay with this one. So this is into the N1. Yeah, which is okay. So in this case, what you really want is so what you really want here, is the total column density times the fraction of N1, which is what you worked out. And so this actually is wrong. this fraction goes between 1 and 0, as you made a graph of it in fact. And so this is the total column density. And so the fraction of the column density in the upper state just follows the same fraction as the density.
And in this fraction is where comes to play the density of...
Because it's changing this, yeah. So it's kind of a mini step, but yeah. This is the two column densities, the two H densities.
These are the two flux ratios.
Okay, great. So
This is when NH2 is 1 to 10 to the 2.
yeah. Okay.
This one is 10 to the 6.
Okay.
So
Yeah.
in the top one, when it's 10 to the 6, the flux ratio is greater. The flux is greater in CS than CO. Right? And in this one, the flux is greater in CO than in CS.
And so this is the main point. So if you look at an interstellar cloud and you measure the flux, and you can just say which flux is greater, and you know whether it's NH2 is 10 to the 2 or 10 to the 6. That's kind of the idea, is that by comparing the ratio of these fluxes, you don't even need to know how big the cloud is. You can estimate its density per cubic centimeter. Okay, so this is not the flux ratio, this is the something else, but it's close, right?
Yes.
But the point is these curves have a difference.
Yes.
And so what that means is that a density of 10 to the 4, there's almost no CS in the excited state. It's below 10% or 10%. So the flux, the more there is in the excited state, the more flux you'll see from CS.
So this one gave me some information about the flux. This graph of the ratios between the NH2 and the ratios of the upper and lower levels will give me information about the flux. And the flux will give me information about the density of the flux.
Which is what people actually do, because you see the flux and then you want to learn the density. That's the direction.
So I have another question. Here, when I have the third point, I have to plot the NH2 density against the excitation temperature. And which formula of excitation temperature I use, because you have this one between the ratios. And
there it is, yeah.
So I use the ratios, I use
and
these columns, these.
Yep, you have the information, yep.
And I just use this.
You can just rearrange that to give you exactly. This log. This is that's G1, G0.
G1, G0
So,
is 3.
so that'll be one log, I think. So, okay, I mean 3 and 1. Is that what that?
3 and the logarithm of the ratios and 1 and 0.
Okay, fine. Yeah, great. Yep.
They call
Yep.
this R.
Yep. Yep. Okay. Yep. Exactly.
So I use this formula and the ratios.
So the two reasons you might, I mean, it seems like extra work to calculate a temperature when you already have the ratio, right? But the reason it's useful is because if you know the temperature of J equals 1 and J equals 0, then that tells you what the temperature is of J equals 2 and J equals 3, because temperature has a well-defined Boltzmann curve, yeah. And it also makes sense when you start thinking, what is the kinetic temperature, what is the radiation temperature, what is the excitation temperature? I mean, when you have this common idea of temperature, you can start comparing them.
All of the temperature.
Yeah, because they all have the same physical meaning, even though one is radiation and one is a molecule. It's weird, but thermodynamically they all have the same meaning. Right? So,
Okay. Oh, thanks.
okay, so you worked it out already?
More or less, I got right the frequency of the monoxide of carbon. Right. But no, sorry.
Yes,
I got this.
that's very big.
I got right this one, and the others say so, but I don't know about this.
Okay, it looks like this is in hertz actually.
Yes.
So it should be so it's 115 gigahertz or 1.1 times 10 to the 11 hertz. So I think your G is
So I take that.
yeah. Okay, all right, good. That was good.
The values are right, or
115 and 490, 490. Yep. Does it work, man?
I think I'm good. Just
Okay, yeah. All right, you're working on it. This is the bad time to distract you. Yeah.
if I have an answer, I call you.
Yeah. No, nearly every word in that email is spelled wrong.
Yeah, everything is wrong, right? Did you say something like that? Anybody from our bank was going to the others conference?
You can say that, yeah.
Because it's a forwarded email, so someone from your side was going to the others. I'm not going to be
What's the ADAS conference?
astronomy, data analysis, software and systems.
You've got a moth
No.
or leaf or something. Okay, sounds pretty boring.
Okay, we have already done this.
Cool.
So we have n1
Okay.
over n total.
So yeah.
So we get something like this. But we have made the plot, and we have a question, because if we use n1 over n0, this goes to 1. But if we use n1 over n total as this one, it goes to 0.5.
Exactly 0.5?
Almost
That's
0.5.
strange. What's going on? So what value did you get for N1 over N0?
Okay, we did this one.
Yeah.
We need this, right? So
Exactly.
this is N1 over N1 plus N0.
Exactly, yep.
So this is basically 1 over 1 over this,
That's, yeah.
but this is this because we have to get that.
Yep. So if this was 0.5, this should become 1, right? That would give you 0.5. So why is N1 becoming N0 at the high density? I think I know the problem. So remember in the question it says use this temperature T kinetic temperature equals 20 Kelvin?
Yep.
Did you use that temperature?
No.
So okay, yeah, it's okay. Yeah, I think I see the problem. Is it one step? So it's going to be in the two level assumption equation. Which is great. Everyone write such nice computer code in. Anyway, so in the notes, maybe you have the equation for the two level.
Over here?
Somewhere in there, yeah. A bit further on. So I noticed that this paper is sugarcane paper. I saw the box of the paper in the office, and it said it's not. Yeah, this one, yeah. So there's three. This is the picture of the approximation. There's three kind of processes.
Yep.
So this differential equation, A is the downwards photon, so minus because it's downwards, it's decreasing the population of the top level. And there's two more. There's this one, which is the up arrow, the collision, and the collisional down arrow. And the important part is you've got actually there's these two coefficients. So Q12 is the coefficient for a collision making it go from the lower level to the upper level, and Q21 is the coefficient for going from the upper level to the lower level, and those are different numbers. So that might be what you missed because they're not completely different numbers, and that they're related by an equation or like the Boltzmann equation because it's to do with velocities.
Yeah, I got this. This is not the same.
Yeah.
We'll have to use this one and hit 20 Kelvin, right?
Because that's where the temperature comes in. Because exactly. Because it depends how fast the molecules are traveling when they collide, whether or not the collision leads to an increase in rotation or a decrease. So there's a temperature dependence in there. Yeah.
Okay, so when we do this plot, do we expect to converge to one?
Well, so one would mean is exactly all the molecules are in an excited state, and that physically that's pretty unlikely. Actually, there should be some
Should do it below?
some left in the lower state. Yeah.
Thank you.
All right. How's it going, man? Okay, so that's the ratio N1 over N total. That's really good.
The value.
Yeah. So what it means is that most of the molecules are in the excited state, but not all. 70% are in excited state, at 30%. Yeah, that's really good. 0.1 at 10 to the 6.
Yes. Does it seem?
C over CS. That's I can check the answer, but that seems pretty good.
Shouldn't it be bigger than 1? Because the density of CO.
So this is C over CS, right?
Yes.
And so livable population ratio and CO is 1.7. Okay, and so the fraction. Oh no, that's the excitation temperature. No, that's the excitation temperature. 1.776. Is there more?
We had this expression.
Yeah.
That was the one I.
Yeah, and so this 1.776, that's N1 divided by N0
0.168.
is that N1 divided by N0?
Yes.
Okay. And 1.776. Okay, enter your graph again. Show me your graph. To the 6. So both molecules should have about 70% or 75% in the excited state, right?
So this should be near to 0.5.
Well, except that it also depends on A and all those other things. But I'm thinking more about this one.
Should I show the code or?
No, that's fine. I've seen your code. It looks really good. But anyway, so this means that 16%. And this means that most of the molecules are in the lower state.
Yes.
But then on the graph, it should be about 70% should be in the upper state. So I think your graph is right, but something is funny here.
But this was with H2 density of 10 to the 4.
Yep.
Let's see the graph. 10 to the 4.
Ah, okay, all right, that's fine then. Yeah, sorry.
So this
Yeah,
is fine.
sorry. Yeah, okay, that agrees with your graph. Yeah, okay, sorry, I take it back. Bless your graph. And so the flux says you're getting more, less, yep. Okay, so you're right. So the density is similar actually, because at 10 to the 6 that's the density. But the other factors, I mean, CO has a bigger frequency, and it's frequency cubed, so that should be so it should be 6 times more, at least 8 times more flux from CO. But the Einstein A coefficient is.
This is 100. This is 2 orders of magnitude bigger than
Yeah.
this.
Yeah, so combine frequency with that, and that gives you the difference.
I mean, these Einstein coefficients are similar to the J1 to transition. Look,
Yeah. Yep.
7.
Yeah. Hopefully this. Yeah.
They are similar.
I mean, it's only different because those J's and the frequency is slightly different, but that's
no,
right.
it shouldn't. Oh yes.
Yeah, yeah. Okay, so in your equation for the flux, the n is the same, and the frequency is more for CO. In fact, it's 2 times more, and its frequency, so it should be 2 times more CO. But then the Einstein A coefficient is 50 times or 100 times smaller,